Have you ever stopped and asked yourself, what is the smallest thing in the universe? For centuries we imagined atoms with a limit. Then we discovered protons, neutrons, electrons. Then quarks. Each time we thought we reached the bottom layer of reality, nature surprised us. But what if we're still not at the bottom? What if electrons aren't tiny solid dots? What if quarks aren't point-like specks? What if at the deepest level everything in the universe is made of unimaginably small vibrating strings? Not metaphorical strings, not poetic strings, actual physical objects so small that they make atoms look enormous. This is the idea behind superstring theory, one of the most ambitious attempts to explain all of physics with a single framework. It suggests that every particle you've ever heard of, electrons, quarks, photons, and maybe even gravity itself, are simply different vibrations of the same fundamental string, like notes played on a cosmic instrument. Today, we're going to explore this idea in the spirit of Richard Feynman, clear, curious, and fearless about asking, does this actually make sense? Does the math hold up? And most importantly, could this be the true fabric of reality? No heavy equations, no unnecessary jargon. Just one powerful question, is the universe, at its deepest level, made of music? Let's begin. Before we can talk about strings, we need to understand the stage they're supposed to replace. And that stage is called quantum field theory. Now that sounds intimidating, but the core idea is surprisingly simple. Let's rewind. For a long time, physicists imagined particles as tiny, solid objects. Little billiard balls. Electrons were tiny dots. Photons were tiny dots. Everything was a dot. But the deeper we looked, the stranger things became. Experiments showed that electrons behave like particles sometimes, and like waves at other times, not metaphorically, literally. If you fire electrons one at a time through a double-slit experiment, they create an interference pattern, something only waves are supposed to do. So what are they? Are they particles? Are they waves? Quantum mechanics gave a shocking answer, they're not either one. They're excitations of something deeper. And this is where quantum field theory, QFT, enters the picture. According to QFT, the universe is not made of particles, it's made of fields. Fields are not objects. There's something that exists everywhere. Think about temperature in this room. Even if there are no visible objects, temperature still exists at every point in space. Or think about the electromagnetic field. Even in empty space, it's still there. Now imagine that every type of particle has its own field. There is an electron field that fills the entire universe. There is a quark field everywhere. There is a photon field everywhere. Even in what we call empty space, these fields are present. So what is an electron? It's not a tiny marble. It's a small vibration, a localized ripple in the electron field. What is a photon? The ocean is the field. The wave is what we call a particle. That's a radical shift in perspective. Instead of saying the universe is made of stuff, QFT says the universe is made of continuous fields and stuff appears when those fields wiggle. And here's something even more fascinating. These wiggles obey strict mathematical rules. They can be calculated with incredible precision. Using QFT, physicists predicted the magnetic moment of the electron to more than 10 decimal places and experiments confirmed it. This is one of the most accurate theories ever built in science. So far, so good. But now comes the problem. Quantum field theory works beautifully for 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, the strong nuclear force. But when we try to apply the same logic to gravity, something breaks. Gravity, as described by Einstein's general relativity, isn't a force in a field the same way. It's the curvature of space-time itself. And when physicists try to treat gravity like just another quantum field, the math explodes. Literally. The equations produce infinities that cannot be removed. In physics, infinity is usually a sign that your theory is incomplete. It's nature telling you you're missing something. So here's the big question. If particles are vibrations of fields, are fields the final layer, or could fields themselves emerge from something deeper? This is exactly the kind of question someone like Richard Feynman would ask, not because the math demands it, but because curiosity demands it. Quantum field theory tells us the universe is a symphony of vibrating fields. But what if those fields are not the instruments? What if they're just the music produced by something even more fundamental? And that is where string theory enters the conversation. Now let's take the next step. In quantum field theory, particles are treated as point-like. An electron? A mathematical point. No size. No internal structure. just a zero-dimensional object, and for many calculations, that works beautifully. But here's the catch. When you try to probe physics at extremely small distances close to the Planck scale, around 1035 meters, those point-like assumptions start to cause serious trouble. Why? Because if a particle has zero size, all of its properties are concentrated at a single point in space. And when you calculate interactions at that point, the math often blows up into infinities. In quantum field theory, physicists developed a technique called renormalization to carefully cancel out those infinities. It works remarkably well. But when you try to apply the same idea to gravity, when you try to treat gravity as a quantum field with a point like graviton, the infinities can't be removed. The theory becomes non-renormalizable. That's a red flag. And here's where string theory proposes something radical. What if the problem isn't the math? What if the problem is the assumption that particles are points? Instead of zero-dimensional dots, string theory suggests that the fundamental objects are one-dimensional strings. Not big strings. Not even atomic-sized strings. We're talking about objects roughly 35 meters long, incredibly small but not zero. And that tiny bit of length changes everything. Because now, when two particles interact, they're not colliding at a mathematical point. They're interacting along a tiny stretch of string. That smearing out of interactions smooths the mathematics. The dangerous infinities that appear in point-particle theories are softened. Now here's the beautiful part. A string can vibrate, just like a violin string. If you pluck a violin string gently, it produces one tone. If it vibrates in a different pattern, it produces a different tone. The string itself hasn't changed, only its mode of vibration has. String theory says something astonishing. Every fundamental particle is simply a different vibrational mode of the same basic string. One pattern of vibration appears to us as an electron. Another pattern appears as a quark. Another as a photon. The mass of the particle determined by the energy of the vibration. The charge encoded in how the string vibrates. Even more astonishing, when physicists analyzed the mathematics of vibrating strings, they found that one particular vibrational mode behaves exactly like a graviton. A massless spin-2 particle, precisely the kind of particle required to transmit gravity in a quantum theory. And here's the key point. They didn't add gravity by hand. It wasn't forced into the equations. It fell out naturally from the theory. That's why many physicists became so excited about string theory. Because gravity, the missing piece in quantum field theory, was no longer a problem to patch. It was an automatic consequence of having strings instead of points. Now strings can be opened with two endpoints, or closed, forming tiny loops. Closed strings are especially important, because the graviton comes from a closed string vibration. In other words, gravity may be built into the geometry of these tiny loops. So instead of thinking of the universe as made of particles, think of it as made of microscopic strands of energy, each one vibrating in an incredibly complex cosmic symphony. Matter is music. Forces are harmonics. Reality is resonance. But before we get carried away, we have to ask, if strings are real, why don't we see them? Because they are unbelievably small, far beyond the reach of any current experiment. At energies we can access, a string looks exactly like a point. Only at Planck scale energies would its extended nature become visible. So from our everyday perspective, particles still appear point-like. But at a deeper level, they may not be points at all. And that tiny shift from zero-dimensional points to one-dimensional strings might be the difference between a universe that mathematically collapses and one that holds together. Now here's where things start to sound unbelievable. String theory doesn't just replace points with strings. It changes the number of dimensions in the universe. In everyday life, we experience 3 dimensions of space length, width, and height, plus 1 dimension of time. That's 4 dimensions total. But when physicists worked out the mathematics of superstring theory, they discovered something surprising. The equations only make sense in 10 dimensions. 9 dimensions of space. 1 dimension of time. Not 8, not 11, 10. If you try to force the math to work in 4 dimensions, inconsistencies appear. The theory breaks. So the natural question is, where are the extra 6 dimensions? Why don't we see them? Here is the key idea. The extra dimensions may be incredibly small. So small that we can't detect them directly. Think of a garden hose lying on the ground. From far away, it looks like a one-dimensional line. You can only move forward or backward along it. But if you zoom in closely, you see that the hose also has a circular dimension wrapped around it. An ant crawling on the hose can move forward and backward, but it can also move around the circumference. To a distant observer, that circular dimension is invisible. String theory suggests that something similar may be happening in our universe. At every point in space, there may be 6 additional spatial dimensions curled up tightly into tiny geometric shapes. These shapes are often described mathematically as Calabi-Yau manifolds. You don't need the equations to grasp the concept. Just imagine space is not empty and flat at extremely small scales, but folded into intricate, compact patterns. And here's something even more fascinating. The way those extra dimensions are curled up determines how strings vibrate. And how strings vibrate determines the properties of particles. In other words, the geometry of hidden dimensions could decide the masses, charges, and interaction strengths of everything in the universe. The shape of space itself may define the laws of physics. Now, we haven't observed these extra dimensions experimentally. They are predictions of the mathematical structure of the theory. But if string theory is correct, the universe is far richer than it appears. What we experience as 4-dimensional reality may just be the visible surface of a much deeper, higher dimensional structure. And that's the strange beauty of it. To make the equations consistent, nature may be telling us reality has more directions than we ever imagined. Up to this point, string theory sounds almost too elegant. Replace points with strings. Gravity appears naturally. Extra dimensions fit beautifully into the math. But the earliest version of string theory had serious problems. One of them was something called a tachyon, a hypothetical particle that moves faster than light. In the equations, the tachyon showed up as a signal of instability. In physics, when your theory predicts a tachyon, it usually means the vacuum you're describing isn't stable. It's like balancing a pencil on its tip, mathematically possible, but physically unrealistic. That was a major warning sign. So physicists asked, is there a way to make the theory more stable, more consistent, more aligned with what we observe? The answer came from an idea called supersymmetry. Supersymmetry, often shortened to SUZ, is a proposed symmetry of nature. And symmetry, in physics, is powerful. Symmetry tells us that certain transformations leave the laws of physics unchanged. For example, rotating a perfect sphere doesn't change how it looks. That's rotational symmetry. Supersymmetry is more abstract. It proposes that there is a deep relationship between 2 fundamentally different types of particles. Bosons particles that carry forces. Fermions particles that make up matter. In the Standard Model, these 2 categories are completely distinct. But supersymmetry says, for every boson, there exists a corresponding fermion partner. For every fermion, there exists a corresponding boson partner. Not identical, but linked through a symmetry transformation. Why is this useful? Because when physicists included supersymmetry in string theory, something remarkable happened. The tachyon disappeared. The theory became stable. And even more importantly, many of the troublesome infinities began to cancel out naturally. In quantum theories, infinities arise because bosons and fermions contribute differently to vacuum fluctuations. But in a supersymmetric theory, their contributions can balance each other, like positive and negative terms cancelling in an equation. This makes the mathematics far more controlled. When string theory incorporates supersymmetry, it becomes superstring theory. And in this version, the theory is not just mathematically consistent, it becomes dramatically more elegant. To raise another fascinating implication, if supersymmetry is real, then every known particle should have a heavier superpartner. The electron would have a selectron. The quark would have a squark. The photon would have a photino. So far, we haven't observed any of these particles experimentally. That's an open question. Supersymmetry might exist at energies higher than we've reached, or it might be broken in a way we don't yet understand. But within string theory, supersymmetry isn't just decoration. It's what makes the structure stable. It's what turns string theory into superstring theory. And at this stage, the picture becomes extraordinary. Reality may be built from tiny vibrating strings, existing in 10 dimensions, governed by a deep symmetry that unites matter and forces at the most fundamental level. Elegant, ambitious, still unproven, but undeniably beautiful. Now we arrive at the real reason string theory exists. Not elegance, not mathematical beauty, not extra dimensions. The real reason is a crisis. Modern physics is built on 2 extraordinary pillars. The first is quantum mechanics, the theory that governs the microscopic world, atoms, particles, radiation, probability. The second is general relativity, developed by Albert Einstein, our theory of gravity, space, and time. And here's the astonishing part. Both theories are spectacularly successful. Quantum mechanics predicts experimental results to astonishing precision. General relativity predicts black holes, gravitational waves, and the bending of light around massive objects, all confirmed by observation. Individually, they work beautifully. Together, they fall apart. Harry's why? Quantum mechanics describes forces as particle exchanges happening in a fixed space-time background. General relativity says space-time itself is dynamic. It bends, stretches, curves. So one theory treats space-time as a stage, the other says the stage itself is alive. That's already a tension. But things get worse under extreme conditions. Consider a black hole. According to general relativity, if enough mass collapses into a small region, space-time curves so intensely that it forms a singularity, a point of infinite density, infinite curvature, infinite gravity. Now bring quantum mechanics into that picture. Quantum theory does not tolerate infinities. When you try to calculate what happens at the center of a black hole using both quantum mechanics and general relativity, the equations explode. They produce meaningless infinities that cannot be renormalized away. The same thing happens if we rewind the universe. At the Big Bang, general relativity predicts that everything was compressed into a singularity, infinite density, infinite temperature. But infinities in physics usually mean your theory is incomplete. They are warning signs. They tell us we are pushing our equations beyond where they can be trusted. So here's the big problem. We do not have a consistent theory of quantum gravity. We do not know how gravity behaves at extremely small scales. One mathematical structure. One underlying ingredient. Tiny vibrating strings. Now, is it correct? We don't know. It remains unconfirmed experimentally. But the problem it tries to solve is one of the deepest problems in science. How do you unify the physics of the very small with the physics of the very large? Until we answer that question, our understanding of the universe is incomplete, and superstring theory is one of the boldest attempts to complete it. So, let's step back and look at all of this in true Feynman style. Feynman had a way of cutting through the complexity and asking the simple, honest questions. If you think of particles as points, you run into infinities. But if they are tiny strings instead, many of those problems simply go away. It's elegant. It's compelling. It solves some of the deepest mathematical headaches in physics. But Feynman would also remind us loudly and clearly, if it disagrees with experiment, it's wrong. And that's the key. Right now, superstring theory is a beautiful, ambitious framework. It unites quantum mechanics and gravity on paper. It predicts extra dimensions, supersymmetry, and a universe built from tiny vibrating strings. But here is the honest truth. No experiment has yet confirmed it. No string has ever been directly observed. We don't know if the extra dimensions are real or if supersymmetric partner particles exist. And that is both humbling and exciting, because it reminds us that physics is not just equations. It's a conversation with nature. We build elegant structures, we explore bold ideas, and then we must test them against reality. Superstring theory might be the key to understanding the universe at its deepest level, or it might be a stepping stone to an even deeper theory we haven't imagined yet. Either way, the lesson is clear. Think boldly, question everything, follow the math, but always check with nature. And that is the Feynman way. So, there you have it. Superstring theory is one of the most beautiful and ambitious ideas in modern physics. An attempt to explain the universe from the tiniest vibrating strings to the forces that shape reality itself. Is it the ultimate truth, or just a stunningly elegant piece of mathematics? The answer is still unknown. If you enjoyed this deep dive into physics, make sure to subscribe and leave a comment telling us whether you want to explore M-theory, quantum gravity, or even more mysteries of the cosmos next. Stay curious and keep asking big questions.